let's take a look at free fall here. And so this is falling objects, what happens when they fall. So free fall. An object is in free fall if nothing is pushing or pulling that object except the earth through the gravitational force. So if the earth is pulling out with gravity, that's fine, but anything else pushing or pulling, it's not in free fall. So for example, drop a ball or kick a soccer ball through the air. And what's important in both of these is we're going to ignore air resistance. The reason for that will become clear later. So some non-examples would be a parachute, because the air resistance is not negligible. So in other words, the air is pushing or pulling on the parachute. Or say, what's another good example? Sliding down a pole. So like if you're a fireman sliding down those stereotypical poles, you've got friction acting on you, you've got the pole pushing you. Or a jet plane has the jets pushing on the plane. So those would all be non-examples of free fall because something's pushing or pulling them. Whereas if I just drop a ball or I kick a soccer ball through the air and I ignore the air resistance, which we can in most cases, you've got that object in free fall. And the thing with free fall is that while in free fall, all objects have the same acceleration, and that acceleration is 9.8 meters per second squared towards the center of Earth. So typically we would say that's down, but it's better to be just kind of specific for now, 9.8 meters per second squared towards the center of the Earth. You'll sometimes see this presented as negative 9.8 meters per second squared. That's fine as long as you always use it away from the Earth as positive and towards the Earth as negative. And you can leave it as negative 9.8. But that will run you into some problems later. We also represent this with the symbol lowercase g. So g is equal to 9.8 meters per second squared. That's another way of looking at this. Now, technically, g can sometimes be treated as just the magnitude and not the direction, but we won't get too fussy on that here. Okay, let's solve a couple of problems here. So the first example, a flower pot is knocked off a windowsill 10 meters above the street. How long does a pedestrian have to get out of the way before getting hit? So we're basically asking how long does it take for a flower pot to fall off of the windowsill. So I'm going to label this here. I'm going to say delta y equals 10 meters just because we're dealing with vertical distance, and we can call our directions whatever we want. So delta y is 10 meters. We know that g is equal to, in this case, actually the delta y should be negative 10 meters because we know it's going to end up at the ground. So we need to say delta y is equal to negative 10 meters because, again, we're calling down negative, and we know that the change is going to be 10 meters downwards. We know that g should also be negative 9.8 meters per second squared downwards because we know in this case it's going down. The acceleration is down, so all these should match up negative, negative, great. And that's also equal to the acceleration a, because again, anytime an object is in free fall, its acceleration is 9.8 meters per second squared downwards. We will prove y or show y in a couple units, but for now, just take it as this is the rule. And then lastly, we have something that's implied here, that the initial velocity is 0 meters per second. If you're knocked off or dropped or something like that, you're starting from rest, right? If I just knock off the windowsill, initially it's just kind of there, and now it's falling. So we've got a change in y, we've got a velocity, and we've got a g, and we want to know how much time do we have. So looking at all of those, we want to use this equation. Delta y equals v naught delta t plus 1/2 a delta t squared. Now here is the one place that I will let you plug in values before you isolate. And that's if you have an initial, if you have something that's defined as 0, or you know is 0. Because that often cleans things up so nicely here. So we know that this whole term has to go to 0 because the initial velocity is 0. So that means we get delta y equals 1/2. Now I'm going to plug in g right here just to make it clear that we're dealing with free fall. But you could leave it as a if you like. And then we'll get 2 delta y over g is equal to delta t squared. So delta t is equal to 2 times delta y over g square rooted. Delta t is equal to 20 meters over 9.8 meters per second squared. And this should be approximately 20 divided by 10. It's about 2, so it's about square root 2, which is 1.2 something, I believe. You can find that out more precisely, but this is our final value. You can, again, go through and actually get a calculator out. I don't have one, so I'm not going to do that here. For our second example, how fast do you have to throw a ball up in the air for it to fall back into your hand 2 seconds later? So what we have here is we initially throw a ball upwards, and we want to know what that initial velocity is. And then we know that it's going to go up, come back down, and eventually be caught. Now, if we throw it up and catch it in the same hand, what that's implying here is our delta y is equal to 0 meters. And we know that our delta t is equal to 2 seconds. So again, it went up and came back down to the same spot, so the change in position is 0. The time is 2 seconds, and we want to find the initial velocity. So what equation do we have? Oh, and we also know that g is equal to negative 9.8 meters per second squared. Because in this case, we're going to call down negative and up positive. So we can use that same equation, delta y equals v naught delta t plus 1/2 g delta t squared. I'm just substituting in the g early. Now, as we said earlier, or if we want to solve for the velocity here, it's going to get a little bit tricky. But as we said earlier, we're allowed to substitute in zeros to kind of simplify things. So this I can write as 0. So 0 equals v naught delta t plus 1/2 g delta t squared. Now, one trivial velocity, well, actually, sorry, never mind about that. Let's divide by delta t on both sides. 0 is equal to v naught plus 1/2 g delta t. And then we get that v naught is equal to negative 1/2 g delta t. So I get V naught is equal to 9.8 meters per second. And this is kind of neat because it shows us what's actually happening at the acceleration. Is basically for 1 second, it's going upwards and slows down and comes to a rest. Then for the next second, it accelerates back downwards and kind of goes through that same pattern or the mirror image of what it did going up.